Welcome to another video explaining the universe using the particle model. Well, today's video is the second video I'm making concerning the idea that those people who are subscribers to Quora, Quora.com, should ask particle and not Quora. Today's subject is a question that was asked concerning inertial and gravitational mass. Quora subscriber asks, if gravitational force acts on all objects in proportion to their masses, then why doesn't a heavy object fall faster than a lighter object? And Quora's first part of their answer, they say it's an excellent question and has a simple but all-important answer. The weak equivalence principle, namely the equivalence of gravitational and inertial mass. This whole issue of it being equivalent and weak deals with the issue of conceptually what they are versus what their values are. There's a video that came out recently in August of 2019 about the black hole, which is kind of interesting news. They claim to have pictures of it. Chris Impey makes a video. It's an excellent video, and I recommend you watch it, even though I may disagree on some points. And he states that inertial mass and gravitational mass are conceptually different, and because they're acting in what seems to be a different environment, and yet their values are close, down to 1 to a part in a trillion. Impey suggests that begs an answer, but he doesn't give any. He gives more examples of why this seems true, but again, there's no physical reason given. Oh man, I'm jumping frames here. Okay, well, Quora goes on to answer what inertial mass is. Inertial mass is a body's ability to resist a force. The more inertial mass a body has, the harder it is to accelerate that body, even if there are no other forces, friction, air resistance, for example, that would hold it back. Is harder to accelerate. Even Newton states, inertia is an innate property of an object. There's something in it that keeps it moving, or keeps it at rest. So I asked the question, can any object on its own resist an external force? No. Can you on your own or myself resist an external force? No. In order to resist an external, you have to anchor yourself to something. So I question this business of resisting at all. He goes on to explain gravitational mass. Gravitational mass characterizes strength by which a body responds. This one's not resist, this is responds to a gravitational field. The more gravitational mass a body has, the stronger the gravitational force that is acting on it. An object's internal mass resists motion, that's inertial mass, resists motion while it responds to a gravitational force. It doesn't say anything about a force here when it talks about inertia. It just says the mass resists, and on the other hand, it responds to a force. It's kind of a mixed bag of an answer. Okay. But then he says these things are happening simultaneously. And his answer is, so you have the answer. A body that is twice as heavy indeed experiences twice the gravitational force. That's true. But it also resists that force twice as strongly because its inertial mass is also doubled. One of my major points is what's real and what's not real, and in this case, mass can't resist any force because it's not real. Mass is not real. The object's real. Mass isn't. The value of mass is a man-made assignment that helps us scientists to measure motion. That's basically one definition that I would accept as what mass is, but it's the value of mass, and its value is assigned compared to the 1 kilogram standard. Okay, measuring inertial mass. How do you do that? Apply 1 Newton of force to an object and measure its acceleration. If the acceleration is 1 meter per second squared, then the mass is 1 kilogram. This is by definition. That is, these are the exact units. 1 Newton, 1 kilogram, 1 meter per second squared is what makes this equation valid, and it is defined that way. And M, in this case, is assumed to be inertial mass. It's not gravitational mass. There's nothing about gravity there, so they call it inertial mass. However, Newton doesn't specify what type of force is used. It could be mechanical, or gravitational, or magnetic. Newton never says. Now, gravitational mass, Newton comes up with the equation for the force of gravity, which includes 2 masses, and both the large m and small n terms are assumed to be gravitational mass. But when Newton developed his gravitational equation, he started with his second principle. That is, he started with this formula, and this m carried right into that m. Then the m in F equals ma, which is they say is inertial mass, shows up in the gravitational equation as gravitational mass, a magic transformation. Could just as well have used a mechanical force and called it mechanical mass or magnetic mass. Okay, but back to the weak equivalence principle. Big physics still does not have the answer that explains what makes the value of inertial mass and the value of gravitational mass the same. They assume that these two events are conceptually different and should not be equal, but they are. That's the coincidence that Chris Impey reports in his video on the black hole. So on to the particle model, and this is G1 inertia in the particle model. The object below is in space far from any other object, and G1 particles are coming at the object from all directions, and it sustains the object's velocity, that is, it sustains its speed and direction. Yes, it's moving, and if the particles weren't there, it would still be moving. But in the particle model, they are there. But when you look at the direction of the velocity of the object, you have G1 particles pushing forward, you have it pushing backward, and basically are assumed to be equal and opposite in all directions when you're far out in space. And so it sustains the speed, although there is a differential head-on force that's slightly stronger than and that's drag that I've talked about. Drag is small because the velocity of the objects are generally much smaller than the speed of the G1 particle. The vertical up and down sustains the direction. It pushes down, pushes up, pushes down, pushes up, and that force, that G1 force from the G1 particle field, keeps it moving in the same direction, not only up and down, but in and out of the page. It would move on its own anyway, but within the particle field, it sustains the object's speed and direction. Now, TPM gravity is different. Again, you got G1 particles coming at the Earth from all directions and looking at exactly one direction, to opposing directions. You have the same number coming in and out, and I've split them for ease of use here. And I'm saying that as these particles pass through most of them pass through, but some of them interact. Small n is the sum that interact and actually push the Earth. The ones that pass through are large n, and they arrive here at the surface of the Earth, and they oppose what's coming in, which is n plus small n. And there is a net force that is proportional to the difference between the two, which is n. So there's a force here created all around the surface because these things are happening in all directions. TPM gravity. Now, in the particle model, these are happening at the same time. They are happening simultaneously. An object flying by the Earth has both inertia and gravity. Here's the Earth, and I drew it small, and then here's an object, like an asteroid coming by. I've made this large so I could fit these numbers in. Now, G1 particles are surrounding this object. Most of them are equal and opposite, except in this direction, there's G1 particles coming through here that are lost in terms of pushing, so there's fewer coming this way. About 1% of, this is an arbitrary number, these are not real numbers. I'm assuming here that because of this is a very small part of this whole surface, that only 1% of it is gravitational, but 99% of it is inertial. 99% of the forces around it are equal and opposite, trying to maintain the direction, keep it moving, sustaining its direction there with a small force to the right, to the left. But when it gets closer to this point, it's closer to the Earth, and the impact, the number of G1 particles lost is higher. And I'm suggesting that there is a 10% of the force here is gravitational due to the loss in this direction. There's an imbalance in this direction. The rest of it is balanced and is inertial in nature. 10% gravitational force, 90% inertial forces causes it to bend more because there's a higher force. And then it moves closer again, and this is 15% gravitational. It's really, really neat. It's a nice concept where way out in space it may have 100% inertial forces pushing it, sustaining it, either at rest or in motion. But as it gets close to an object, it slowly changes part of it to gravity, part of it inertia. And it gradually changes. As it, in a sense, moves incrementally, these changes are very subtle and incremental, and to me it's very elegant to see how the dynamics of these forces, gravitational force and inertia, is working at the same time. Now, the Quora never really answers the question. The questioner wants to know why they accelerate the same, and here's one possible answer. It's math. You start with Newton's second principle, and his question was about gravity, so you substitute for F the gravitational equation, you get this. So in this initial equation, you have one unit, a small m here, and mathematically you can cancel it out. However, when you do that, you have an equation with only one mass, and there is no acceleration with one mass. You need two. But nonetheless, mathematically, they are equal, and mathematically, they cancel. But if you double the mass, it doubles for the force of gravity. It doubles for this term in the equation, and mathematically, they cancel out. So whether it's double or half, the acceleration is the same. Force can be mechanical or gravitational, and there's no need for a resistive force of inertia to cause both objects to have the same acceleration. Admittedly, they claim this is resisting. That's where they get the resistance from. But in the particle model, there is no resistance. There is a sustaining of the object's motion. An unbalanced G1 field causes a gravitational force while the balanced G1 field sustains the speed and direction of the object, and it's all based on the same mass m. And it's happening simultaneously and very smoothly as the object glides through space. The percentages of these subtly change depending on its position. According to the particle model, the concepts are the same because they involve identical interactions, and it is verified by the fact that the value of the mass is the same. My name is Bob D. Hilster, and I am your particle model guru. If you have a question, don't ask Quora, ask Particle. You can do that by clicking on the little bell at the website and leave a message or question there, or you can I'll leave you the email address for Particle Guru. Thank you for your attention.